Optimal control is a versatile method to generate highly dynamic motion behaviors and maneuvers by exploiting system dynamics and operating over a long time horizon. However, the problems are often highly nonlinear as well as non-convex, and without a proper initialization, the algorithms tend to take a long time to converge or can easily get stuck. As thus, near-optimal initialization from offline experience is widely explored. However, directly applying machine learning to a dataset of offline gathered solutions often leads to poor generalization, as the underlying solutions can contain discontinuity and multimodality. A cart pole can swing up from the left or from the right. Similarly, in this humanoid manipulation example, the individual compartments of the shelf create discontinuities in the solution space. Likewise, the quadrotor in this example can fly around an obstacle following several different paths. If we do not explicitly take the multimodality of the solutions into account, learning methods may smooth across the different solution classes, resulting in poor initialization guesses. We can observe this, for instance, by looking at the control trajectories for the cartpole swing-up, where, without the class sensitivity, the information in the dataset vanishes due to the multimodality in the solution. In our work, we take a mixture of experts approach to train a local expert per continuous subset of examples in the dataset. Here too, we use a persistent homology to inform the clustering based on the topology of the solution space. We introduce a novel method for clustering time series data based on persistent homology to identify multiple modes and discontinuities among continuous trajectories within a dataset. For scalability to large datasets of time series data, we leverage a segment-to-segment distance for filtration and use a pairwise trajectory distance for clustering. We introduce a procedure based on half-life to automatically extract the number of clusters from the persistence of cohomology groups. This allows our method to automatically cluster data without further user input. We demonstrate that this method can be applied in state spaces of different dimensionality and is also applicable to high-dimensional task spaces. We evaluate the scalability of the method with respect to the number of trajectory samples and the number of time steps per sample. Using the clustered data from our method, we train a generative mixture of experts model and show that multimodality-aware warm start predictions outperform learning without the clustering for warm starting a dynamic optimal control task in a complex environment. We apply our approach to the quadrotor dataset shown earlier. The persistent homology selects 6 solution classes. We show these here in color. It is immediately clear that without modality awareness, combining the different samples would result in a path going through the environment obstacles. To visualize this more clearly, we now compare our mixture of experts model with class-agnostic learning using a multilayer perceptron and k-nearest neighbor regression. We further compare the commonly used optimal control cold start, where the control trajectory is a sequence of hovering commands at the initial state. To explore the learned models, we now vary the query point along the x dimension. Here, we visualize the state trajectory prediction in blue, the rollout of the control trajectory prediction in orange, and the final optimized state trajectory in green. Note that the difference between the blue and orange trajectories are the dynamic defects the solver needs to reduce or close. The further the blue and orange trajectories are apart, the more iterations are required, or the more likely the solver is to getting stuck in a local minima. Note the magnitude of the dynamic defects for the class-agnostic learning approaches. We now perform a benchmark with randomly sampled initial states. We compare the iteration and time to convergence as well as the final cost. Looking at the convergence versus iterations, we can observe that class-agnostic learning, despite a low initial cost, performs worse than a cold start as the algorithm closes the gaps of the dynamics defects, and that our method has both a low initial cost as well as converges faster than the other initialization methods. This observation is even more pronounced when looking at the convergence versus time. Here, our method converges significantly faster than the cold starts, as it requires fewer line search steps, or minor iterations, as the dynamic defects are smaller. Finally, we find that our method outperforms the class-agnostic learning methods as well as a cold start by requiring fewer iterations, resulting in a lower final cost with fewer outliers, and achieving a higher success rate.